Hey there, my name is Seth Juarez. I work for DevExpress. A warning, if the Microsoft people come in here and tackle me down, it's because I'm not an MVP. Everyone else is an MVP. Additionally, I do not have an interesting accent like everyone else. I apologize for that. I'm sorry. But today we're going to be talking about machine learning on Azure. You'll see that the Azure part is actually the easiest part, and so the majority of this talk is going to be focused primarily on what is machine learning, and you'll see at the end that the part that we do with Azure is super easy and super intuitive once you have a couple of things going on there. If you have any questions or you want to complain at me, you can ask on Azure Conf. I think right now there's at least one person watching. That's my mom. Hi, Mom. Thanks for watching. And if there's more people, good. Put some question ups on Azure Conf using the hashtag AzureConf, and I'll try to answer them as they go along. There's not a lot of time. I'm going to be going over quite a bit of stuff. There's going to be some mathiness, and that's okay. We can deal with that. So, agenda for today, we're going to talk primarily about data science, what it means to predict, what the process is to do these things, what models you can build, and then how you can use this stuff on Azure. And I think the coolest part about Azure is you sort of lose this constraint of having your local resources be the bottleneck. Now you're literally doing stuff in the cloud. So it's a pretty exciting stuff. So a word about this stuff. Often I always get this question after any machine learning talk. It's like, hey, Seth, I have this really good idea to predict stock prices. You and I can be rich. And every time I'm like, yes, no one has ever thought of that, and they're not doing it right now. Here's the thing. In your particular problem set, it might not work. The scientific method, you recall, starts with a question. And then you move on to some research. You think of a way to solve it, you try it out, you analyze it, and then there's a conclusion, and usually you have to go back and re-research, or you have to go back and have another idea on how to solve this. And so these models they're experiments. You have to try it out in order to make sure it works. But there's a certain pattern that you can follow. And again, just try stuff. I'm going to show you a couple of models that may or may not work. And so if I get emails that say, hey, Seth, I tried this and it didn't work, I will say something like science. A lot of times you'll have questions of like, what should I use? The answer is science. You got to keep trying stuff until you get it. So let's talk about machine learning in general. And I'll preface it with a story. Imagine you work at a bank and the salesperson comes in and says, hey, I have a really good idea. I want you to scan checks, but you need to flip the checks upside down. And say you work for a really small bank, and your small bank has sort of a black stripe at the top. The check does. And so your algorithm pretty much has to say, if black stripe at bottom, flip. Pretty easy. But then the salesperson comes in again and says, hey, we have a really big customer, and he wants a picture of his cat on the check. Well, now you have to say, if black stripe at bottom, else if cat upside down. And I don't know, I mean, there's probably code for that somewhere on GitHub, so take a look. If cat upside down, then flip. And so you have to go in there and tweak. And then again, he comes back, the salesperson, and says, hey, we want to be able for the person to put any picture on the check, and you got to be able to figure out if it's upside down, right side up, or whatever. Do you have algorithms like this where you go in and you have to tweak, you have to add another if statement, you have to add another else statement, you have to go in there and change 0.8 to 0.7, and somehow it seems to work? If you have algorithms that you've built that do this, these might be really good candidates for machine learning, because primarily what you're doing is you're tweaking. And machine learning sort of flips the idea of you having to write an algorithm for a problem to instead you give the computer examples of what the right thing is, and it figures it out. It changes the whole process of development, really, I think. The central issue of machine learning, again, is generalization. And there's sort of two areas-ish. I mean, there's also a bunch of other stuff. But supervised learning is all about prediction, and unsupervised learning is all about sort of finding the nuance in a large set of data. Primarily, we will be focusing on the supervised learning problem here. There's other talks that I give on the unsupervised learning problem. You can look those up. and on any of your favorite search engines. But supervised learning, you give it the right answer and a lot of examples and it figures it out. Unsupervised learning is, here's some data, try to make some sense out of it. Is there any structure? Can we compress this anyway? That's what unsupervised learning is. Here's a really neat application. The Connect is actually an example of a supervised learning problem. The feature selection that they did for this is absolutely amazing. I saw a talk on the persons that made the algorithms to detect where your body is, and it's absolutely fantastic, and it uses actually one of the algorithms that I'm going to show you, a better version of it, of course. And then an example of the unsupervised learning, I kind of put my head down in shame. This is my Netflix queue. So you can tell that I have kids, or maybe I don't. In either case, this is an example of the unsupervised learning problem where Netflix is able to group stuff in a way that will provide recommendations to you when you're doing stuff. So the first question that pops up, what are the advantages of using machine learning in Azure? You'll see at the end when I do the demo, because you're constrained by memory and by space when you're working on your local machine, and then when you're working in the cloud, you don't have that constraint. There's other things. There's other things that you can. There's other examples of neat applications. I worked on the machine translation problem when I did some research. It's actually a really hard problem. There's a bunch of cool stuff. Machine learning really is kind of taking over. The whole notion of data science is pretty exciting right now. Okay, so let's talk about the notion of prediction, and let's see what we can learn from that. I was told not to use pictures that are unlicensed, and so I am using a cadre of pictures from the Office Online. So these are some really good pictures. Let's talk about classification or prediction. There's really three kinds that we can subdivide this into. The first is binary classification, where we're deciding between one of two things. Yes, no, male, female, A or B, whatever. Multi-class classification is the situation where we're deciding between a finite set of things, categorical type things, A, B, C, D, 1, 2, 3, 1, 2, 3, 4, teacher, secretary, student, anything that's finite. And the last one is when we're trying to predict any real value, and that's usually called regression. Now here's the interesting thing. If you can solve the binary classification problem, you already have a solution to the multi-class classification problem. How so? Here's the interesting thing. Say you're trying to decide between A, B, C, D, E, and F. What you can do is you can make a binary classifier to decide between A and B, A and C, A and D, A and F, and so on, and you can pick the winner. So you have a bunch of classifiers, binary classifiers, that you can use to make a multi-class classifier. This is called the all versus all strategy of multi-class classification using binary classifiers. There's another one too. You can say, is it A or something else, B or something else, C or something else. That's called the one versus all method for a multi-class classification. So let's assume for a second that with binary classifiers you can solve the multi-class classification. While there are multi-class classification algorithms that are just inherently multi-class, you can use any binary classifier to do a multi-class classification as well. It's pretty cool. All right, so there's a four-pronged process that you need to follow whenever you're doing machine learning, and it's pretty standard. And once you understand this process, when you go to machine learning on Azure, you'll see how that process is ingrained in sort of a workflowy kind of way. The first thing is you always have to start with data. What are you looking at? And particularly in the supervised case, you have to have a set of data with a right answer. We'll see a little bit more on that later because we're going to hammer this four-step process every time. The second is you have to clean your data, and you have to put your data in a state where the algorithms can work. So you have to do some cleansing. There's maybe missing values. Maybe you have to transform. Maybe there's two columns that really should be one, and you have to do some kind of formula to get both of them. And then there's the maths. In the United States, we apparently only have one math. Everywhere in the universe besides the United States, it's called maths. Apparently you have more than one. Good for you. And so here's the next thing. Once you have done this conversion, and now you have it in a state where the algorithms can take it, what you need to do now is you need to make some models. And these models are the things that have the predictive power. In essence, you're taking your data and you're making this thing that's smaller than all of your data, but that has predictive power to give you the right answer, to tell you if your check is upside down or right side up. And then finally, you use that model to make predictions. So, this is the four-step process. Data, clean, model, predict. Data, clean, model, predict. And remember this process, because once you get a good feel for this particular process, you'll see on Azure that once you know that this is the four steps, you'll know where to go and how to drag stuff in. So it's pretty cool stuff. Let's review it one more time. So let's pretend we're gonna work with some data. You work at a tennis shop and you work at a tennis court and you want to know if people are going to play or not play tennis. So you have some weather information and you want to be able to staff your particular tennis court accordingly. So you have some data like so. You can see it on the slide right now. The terminology that's used for this is their label is the thing we're trying to predict. The features are sort of the things we're using to predict the label or the columns in your database. And then the values are the actual instances. So imagine the features as your class and the values as your objects that are instantiated from your particular class. And so in this example, you can see that we have the outlook, the temperature and whether it's windy or not, and we actually have whether people have played or not. And the machine learning problem is given a data set that's labeled, meaning we have a set of features and a label, and then a series of instances of these XY pairs, X being the features, the set of features, the values of the features, and Y being the actual class. Once you have those, you have this XY pair, given a brand new X or a brand new set of feature values, how do we predict Y? That is, in a nutshell, the supervised learning problem. But in reality, your data will probably look more like this. And this is, people type stuff in and your data is not all the way clean and you're missing a particular something. You have to clean the data first. And in order to do that, you need to clean it, you need to replace things, you need to standardize. For example, Turtle Cloud in Outlook probably should be something like, I don't know, this should actually be Overcast instead of Turtle Cloud. Or if it's empty, what do we put? Should we just say it's low or high? I don't know. Notice there's a kind of here. What do we do with that? And that's really the interesting part of machine learning. Not really. Actually, there's a term for this in computer science called yak shaving. And that's the majority of a data scientist's work. Incidentally, I didn't say this to start, but after this particular session, you can go to your boss and tell her, I am now a data scientist, automatic raise. I'm telling you, you guys, send me checks right now. Automatic raise. Most of the work your data scientists are doing in that fancy room they have that's closed and really nice is yak shaving. It's converting the data into something that the models can actually consume. And here is the office picture that I found for a yak. It's actually quite good. So that's a lot of the work. The thing that's nice about this is that the machine learning on Azure tool does a lot of this cleaning for you. It's pretty cool. We'll talk about it when we get to that particular demo. All right, so the other thing that once you clean it and you do some transformations, that has to be put into a format that the algorithms can digest, which is maths. And in this case, the x usually is converted into a matrix, and the y is usually converted into a vector. Machine learning turns out to be a lot of glorified counting. And so that's one of the cool things. So from now on, when we talk about these things, I'm going to talk about these things in terms of numbers. In other words, when we're talking about a set of features and their instances, I'm going to assume they're all numbers from here on out, because the process is going to go ahead and convert them to the actual numbers. And then remember, the first step is data. The second was clean transform maths. The third is now we need to make a model. So looking at this particular table, how would you predict? And the interesting thing is, and this is fun to do, right? If we look at overcast in this case, you'll see that they're all set to play. So we can assume that when the weather's overcast, people are going to come and play. We should staff people. Here's the other thing. Notice that when the temperature is high, right, you can see that right there, temperature's high, they don't play. Sunny and high, they don't play. In this case, windy really doesn't have an effect. And then you can go on and do this. Now, here's the thing, though. What if you have 15,000 columns or 15,000 features and 3 million rows? All of a sudden, trying to figure that out becomes pretty daunting task. The machine is pretty good at figuring out the kind of models that it can build. In this case, this is the decision tree that the algorithms produce in order to show you how predictions will happen in this particular set of data. And then finally, once you actually have the model, it's time to do predictions. And so here's the model you've already built. You get a brand new example. Let's see, when the outlook is sunny and the temperature is low, so outlook is sunny and the temperature is low, looks like we are going to play. There you go. Right, and once you have the model, it's pretty easy to do the prediction. Now, a word about these things. There's a couple of ways to train these models. There's an online methodology where you give it an example and then the right answer, and then it updates its model, and you keep, this is called the online methodology, where you keep on giving it examples. And then there's the batch mode, where you give it a whole set, a slew of examples, and then it comes up with a model. That's the batch mode. The cool thing about machine learning on Azure is if you're doing a batch mode with millions and millions of rows, it's okay. It's happening in the cloud, and it really doesn't affect anything on your machine, which is really cool. Okay, so let me show you a little bit here how I envision this. I built a REPL as an example set to help us sort of understand how these things happen, and I show you a way that I like to do it. And then you'll see how on Azure it's even easier than this. So here's an example of, here's the tennis data set that we just looked at. I think I added humidity to it. And if I scroll down, you can see I have a bunch of data. So we're going to run this here, snip 0, and it's going to load up all of the data. Now let's move to snippet 1 here. Notice that in the process of cleaning or transforming data, you have to find a way to describe the data that you're working with, and you're going to have to do this on Azure. Here's, in this case, I'm using a descriptor. And notice that when you're looking at the tennis data, it's just what you would expect. It's just the set of data, and this is the label. Right? The descriptor here just tells it what we're looking at. In this case, we're trying to predict play, and we have a set of features that are going to help us predict that. So I think I'm on snip number 2. So notice that snip 1 is part of setting up the data. Snip 2 is getting it into the maths. Notice that I have x, and x is a matrix, and y is a vector. And once you have x, right, you can do all sorts of crazy stuff like, I don't know, find the eigenvalues of this particular product of the matrix. You see what I'm saying? And so the idea is once you've got it into a form that the algorithms can understand, you're pretty much done. And again, remember, we're assuming from here on out that our features are all numerical because we found a way to convert them to that. Okay, I think we're up to snip number 3. There you go. Here is the model that it built. And I'll show you later on that this model will change based upon the data, but it just made it. It's a model. And you can see that when you're working with these things in Azure, it's the same kind of thing. And then finally, we need to be able to predict. Notice that we're giving it a new example, and then we're saying, hey, predict, and then let's see what it predicted. List of P, you can see that in this case, we should not play, right? And so there's the fourth step. You have your data, you do some transformation, cleansing, convert it to math, or you convert it into something that the algorithms can understand. You make the models, and then finally, you do prediction. So those are the 4 steps. And you can see the code for that is not very difficult. I mean, in this case, this is a machine learning tool that I wrote, but the one on Azure is much better because you have so much more space, so much more memory. It's fantastic. So I am going to close this down, and let's head on back to some of these slides. Okay, so the question now becomes, how do we build these models? And I'm going to tell you right now, we're going to be doing a little bit of math, and it's okay. Math is our friend. Math is just a really short way of writing a couple of paragraphs. And so when I show you some equations, they're not scary. Trust me, I'll explain them to you. So let's talk primarily about a linear classifier. We need a way to separate items in classes, right? So because again, remember, we're going to focus on the binary classification problem because that one we can convert over to multi-class. I won't talk about regression because there's a number of methodologies for using regression, and I like these kinds of classifiers. So linear classifier is we need to find a way to separate 2 classes. We need to find what's called a decision boundary, and so I'm going to show you a good way to think about it. So I'm going to open Excel, and I'm going to show you a machine learning problem that I built. How many features does it have? Well, just one. How many labels does it have? Just one, right? Because we can only do prediction on one label. If you want to do 2 labels, then you have to do another model. So how would you go about doing a prediction in this case? Well, I've often got the case where it's like, hey, why don't you take an average and then see what it compares to with the average. Maybe you can add them all up or do some other crazy thing. Let me show you a real simple way to do this. So I'm going to go to the data here, and I'm going to sort this by feature and hit OK. Notice what happened, right? Oh, looks like right here, there's a decision boundary, all right? Anything that is less than 6 turns out to be true. So this machine learning algorithm would be return x less than 6, right? That's the machine learning. Notice in this case, we've been able to separate this set of features, which are points on a line, right? Because it's just a single line, and then we start all the way at the lowest number, go all the way to the highest number. This particular separator happens to be a single point. Okay, well, what if you're working in more than one dimension? So let me open this up, and let me load this. So in this case, notice that now we're working in 2 dimensions. Well, how do we separate this? Well, it turns out that you can make a line and separate. Are you going to make some mistakes? Yeah, but that's okay. Are you going to find the best perfect line? Maybe. I don't know. But the idea is, in this case, you have 2 features, and the label is red or blue. And so you can see, I mean, this is a simple line. So let's talk about how we can actually generate a line to separate features. So let's go back to the slides here. Let's go back to our old school linear algebra days, and let's talk about the dot product. You remember the dot product between 2 vectors as you multiply the first one, add it to the multiplication of the second ones, and then you get this number, which is the dot product. But here's an interesting relationship that's really cool. The dot product between 2 vectors always, 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 always equals 0 when the cosine of a particular angle equals 0. And you remember that the cosine of 90 degrees happens to be 0. And so irrespective of the magnitude or how long these vectors are, because a vector can be a point on a graph, or it can be this thing from the origin and an arrow out. Any two vectors, when they're perpendicular to each other, their dot product will be 0. And another interesting thing, the set of all vectors perpendicular to another vector forms a line. So if you have this vector here and you get all of the vectors that are perpendicular to it, you have this line. Right? And remember, when we want to separate things, we want to make a line. And so now we can represent a linear separator by using a single vector. And another interesting thing is that the dot product between two vectors will either be 0, negative, or positive. It turns out that when the dot product between two vectors is negative, it's on one side. When it's positive, it happens to be also on the other side. And so now what we can do is, if we find this magical vector W, that we can do the dot product against a new example, right? Because that's what the machine learning problem is, to get a new example. We can figure out if it's negative or positive, and we can assign that to either the negative or the positive class. And so, in short, one vector will be able to separate your data. Now, when we're thinking in two-dimensional space, it kind of makes sense, right? Because it's a line. When you go to three-dimensional space, it's now a plane. When you go to four-dimensional space, it becomes some kind of cube thing. Five-dimensional hypercube, six-dimensional hypercube, because we kind of run out of words after that. There are problems that I've done that had 15,000 dimensions. And it's okay, because linear algebra does not care about the dimensionality of the problem. Only your CPU and RAM do, it turns out, and that's where Azure ML comes in. All right, so Perceptron is pretty easy. Incidentally, I use this refrigerator because Perceptron was invented in the 50s, and it sounds like some old school refrigerator, and that's why I put it there. So that's it. Let's make a line, use a single vector, take the dot product between it and every other example, and then move the line so it has the best classification. Let me show you what that looks like here. So here, the machine learning algorithm is going through and saying, all right, I'm going to look at every example, and I'm going to move the line when I make a mistake. And it's going to keep doing this and keep doing this. At the end, it takes the average of where it stayed still the most, and it's found a line. And that's the algorithm in short. It's an update algorithm for those of you that are math wonks. It's kind of like a gradient descent. It's trying to find the optimal line. Kind of. And the cool thing about this algorithm is it can be done online, meaning you give it an example, update or not update. And it's pretty simple. So here's a question. I did that. Here's a question. Before I go to the next question, here's another way of thinking about it. You have a new example, you convert it to math, and you clean it. You take the dot product of those examples with, for example, these numbers, and then you get an answer whether you play or not. There is a bias term that's added. You remember in your maths class when you did lines, you had y equals mx plus b. B just helps it shift over, the lines shift a little over to make it a little easier. Let me show you again what that looks like in real land. So we'll go to Perceptron here. Notice here's a bunch of students. We're trying to predict whether they're good or not. I'm going to generate a model. There it is. You can see that this is the weight vector that it learned. And now when we want to do predictions, let's see. This guy has one friend now, and now he has a grade F. And you can see that the dot product happens to be negative, which means that Jens is not good. Let's go up to A and let's give him 12 friends. And let's notice that Jens is good. You can see that. And here's the other thing that's really cool, right? Notice that even if this algorithm doesn't work, at least mathematically you can see which features have the most influence on positive or negative things. So grade is a strong influencer, and that's one of the cool things about this particular algorithm, is that at least it will give you some of the weights to let you think about it. Now, again, look at this Perceptron sort of diagram that I'm showing you. You get a new example, you push it down, you multiply it, and then either it's positive or negative. and that will tell you what class it belongs to. That's to perceptron. Well, okay, that's all good and well, but you tell me what line separates this data. Everyone always shouts out in my demos, circle. Well, it turns out circle isn't a line. So what do? I want to force the issue with linear models. I want to do a linear model. So what can I do? Well, there's two options. I can transform the space I'm working in, or I can use a linear model with augmented predictive abilities. The first happens to be what are called kernel methods. The second happens to be called neural networks, and you've heard that. And so I will motivate these right now. So what we're going to do for this particular algorithm right now, for this particular set of points, is we're going to project the data from 2 space into 3 space. And the way we're going to do that is we're going to say, okay, x is now going to be x squared, y is now going to be y squared, and z is going to be x times y, modulo some constant square root of 2, I think is what it is. Let me show you what that looks like when you do that. So I'm going to go here and I'm going to load up some Python, because everyone loves Python. From import star example graph 2. Okay, so here is this thing. It's similar to what you saw before, where you can't do a line. Remember, we're going x squared, y to y squared, and then z is going to be x times y. Watch this. Boom. Notice what happened when we put it into 3 space. So now we have the same data projected into 3 space, and take a look at this craziness. You can separate this with a line now. Happens to be a plane. When you pull, imagine spilling something on your sheet. Say you were drinking a Dr. Pepper, which is quite tasty. You spilled it on your sheet, and say the way to clean it is you pull the sheet up and you whack off the dirty part. When you put the sheet back down, what's going to be left? That's right, a circle. And these are called kernel methods. Now, here's the interesting thing. Now it's going to get a little mathy, but that's okay. It's okay. Now this kernel method is like perceptron, except now we're taking O times W, which is outlook, whether it's windy or temperature, and then that's going to decide what's happening when we do this. The problem becomes, well, if you have 3 features, it becomes 9. If you have 4 features, it becomes 2n plus n. You see what I'm saying? It's exponential. It's not exponential. It's order n squared when in number of features. So if you have n features, you're going to get somewhere in the order of n squared. If you have 15,000 and you square 15,000, it's not going to fit. How do you solve this dimensionality problem? Well, let me show you something that is absolutely crazy, that was discovered not very many years ago. People found a long time ago that the best W to separate it happens to occur when you minimize W, subject to these constraints. And this is easy, right? This part right here, this is the W vector we learned. This is the example, right? These are all the examples, and this is the bias term. Notice that this will either be plus or minus. This happens to be the answer. This will either be plus or minus. When they're both plus, the answer is positive, which means we got it right. When they're both minus, the answer is still positive, which means we got it right. So it's got to be greater than or equal to 1. Now, whenever you have a numerical optimization problem like this, you have to do some crazy math. In order to do that, the equation will become this. You have to add what are called Lagrange multipliers, and then you have to do some calculus to do that. But notice that this particular problem, when you're looking at this formula, however crazy it might look, the x value right here, this formulation happens to be just the dot product, right? And this dot product was the same dot product we used for perceptron. So you can make a function to produce the dot product. Right? Remember, just a reminder, in the perceptron algorithm, the dot product was what made it special. And so now we can store the dot product inside of what's called a kernel matrix, and then instead of actually making the dot product between 2 things, for example, the x in the new space, which is going to be huge, Instead, we can just store the dot product. This is the basis for what are called support vector machines. Because the alternative formulation that you've just seen, the output would tell you the set of points that are along the decision boundary, and you can use those points to make the prediction. Here's the crazy part. The one we just did is called the polynomial kernel, where we did x squared, y squared, square root of 2x times y. This kernel, the RBF kernel, right? When the sigma is equal to 1, we are effectively projecting into infinite dimensional space, finding a linear separator in infinite dimensional space, and projecting back. I'm going to let that soak in a little. That's right. When I understood this, my head exploded. And so now linear models, which are just lines, can actually be used to separate complex things when we project first, in a finite way, by the way. Notice that can be computed in a finite way, and you can make this matrix K, which happens to be symmetric positive definite, which is even better. And then you can find lines in that space that separate it, and then use the line in the augmented space to make predictions. All right, well, what if that doesn't work? That's okay. So this is neural networks. Wanted to talk a little bit about neural networks here. Because remember, if that doesn't work, let's try something else. Now, looking at this is an example of a neural network using outlook, temperature, and windy, and then a bias term like before. Notice that this is similarly and eerily familiar, right? This little hidden part, H1, looks like a mini perceptron. And indeed, that's what it is. You have 3 perceptrons that are feeding into H1, H2, and H3. And then the crazy part is once you've done that, and then you sort of feed them back out, in these intermediate nodes, we're going to add a function to either make it less, to dampen it, or to output that a little bit stronger. These are called sigmoidal functions. They have to be differentiable, and usually there's like a tanh function or some other function that you can use. So instead, now we're taking 3 perceptrons, and we're creating a function around that perceptron, and then what we're going to do is we're going to aggregate them again by by adding these things and multiplying them together. And then the positive or negative will tell you whether or not you should actually play or not. And this is called a neural network. Now this particular problem is not as optimizable as it is optimizable. Here, let me give you an example. Remember the function x squared? It makes the u. If you want to find the best point or a critical point, you remember from calculus, you take the first derivative, set it equal to 0. For x squared, you remember it's just right at the bottom, right? You take the derivative, which is 2x, you set it equal to 0, and when x equals 0, you're at the bottom. There's other functions that are not like that, like x cubed, right? Notice there's no optimal point because they sort of goes off forever on both ends. But you have intermediate optimal points. Turns out that the neural network objective function that you're trying to optimize is not convex, which means it does not have a single optimum, so you got to find one that works, and so there's a number of strategies to do that. There's a couple of algorithms to do that. In fact, I think in the last Tech Ed, there's someone that was talking about how to optimize these particular things. Okay, so linear methods, perceptron, that's the easy one. What if we can't make a line? Well, let's change the space, SVM. What if we can't make a line? Well, let's change the function that's still iffy linear. That's neural networks. All right, so this is the final model that we're going to go through real quick, and then, now that you've seen this, you'll be able to see how to do this in Azure really quickly. All right, so you remember this decision tree that we set up earlier. How does one make that? So there's this thing called information gain with entropy that lets you figure out how these things work. Now, here's the best way to think about it. So you have outlook, temperature, and windy. Entropy tells you how messy a particular column is. So the answer is Y. We want to know how messy is Y. Okay, how messy is Y if we know what the outlook is? Does it decrease it by a lot, right? And so H of Y is how messy is the answer. H of Y given A is how messy is the answer if we know A. Now, if we know A and it's still the same as messy, That means that A has not given us any information about Y. So if the answer is 0, hasn't really done anything. So the higher the answer, the better. Okay, so let's take a look at this here real quick. So we'll go back to this decision tree. Notice we have sunny, temperature, and windy. Let me zoom in here so you can take a look. All right, so Outlook, here's the information gain for Outlook. Notice it's 0.3601. Here it is for temperature. Here it is for windy. Looks like Outlook wins, and then when you go by, you can see that it makes this decision tree. Well, let's change some stuff around. Well, obviously that makes a different decision tree. Now, this algorithm, I'm showing it to you primarily because it helps understand when you actually do them on Azure ML, they have better ones. They actually have linear combinations of decision trees, and they have this thing called decision jungles, which lets these things sort of go back on themselves, which is really cool. All right, I think I've shown you a lot of machine learning stuff. We talked about support vector machines, neural networks, and decision trees. Do they work? Well, I don't know. You have to train them. And this is the way you do it. You get your set of data, you partition it somehow, you use some set to train and some set to test. I put 80 and 20 there just because, I don't know. You can use whatever you want to do that. This is typically what I do. So let's put it together with Azure. All right, so if you are on Azure, remember, just a reminder, because this is very important, because I think if you remember this, the 4 steps, it will make a lot more sense when you're doing these things on Azure. You have your data, you do some cleaning, you make a model, and then you do prediction. All right, so let's go to Azure here. Notice to do a machine learning thing, you go down here to machine learning. I have 2 that I've set up, one that's clean and one that I've done some testing. To make a new one, you just hit the plus, you go to quick create, and then you give it a name. The other thing you have to do is you have to give it a storage account where it can do its work, right? And that's the cool thing. All right, so I've already done that. So feel free to go do that. I'm going to go to my robots workspace, and I am going to load it up. Okay, so we're in the robots workspace. Now, here's the cool thing with Azure ML. They know it's data science. And so you can see that these things are called experiments. And that's what we're going to be doing. So let's go to experiments, and we're going to make a brand spanking new one. So we're going to go to experiment. There it is. I'm going to call it the income experiment. There's a number of things you can do to get data into Azure ML. The first, here it is, the data input and output. There's this thing called a reader. Let me drop it on there. You can pull from any number of sources, like an HTTP call to a CSV file, or SQL Azure, Azure Table, Azure Blob Storage, Hive Query, or Power Query. So the data doesn't necessarily have to be in there. You can use readers to pull the data into the processing of the experiment. Also, if you want to get started, there's some really interesting saved data sets. I'm going to go ahead and just use the adult census data set. Now, let's go in here and let's take a look at what this looks like. Remember, the first step is data. So we need to look at our data. When we're looking at it, we need to see, all right, what am I going to use? The first thing is we want to be able to predict whether someone makes less than or equal to 50K or greater than 50K given all of these features. Here's a cool thing. When I click on this particular column, you can see the age distribution, or you can see the work class distribution. Notice that this column, they're all mostly private, and so it's not going to tell us much, so maybe we can ignore this one. Final weight, notice you have that there, and you can see that for numeric features, you have the standard deviation, you have unique values, you also know how many things you have. We're working with 32,000 rows and 15 columns. And then we have education. The other thing is if you want to do comparisons, you can move this over, and then we're going to go to work class. And you can see that maybe there's a correlation or maybe not. It just depends. So this is the part where you're actually trying to clean your data, right? So we have our data, and now we need to figure out how we want to clean it. Well, I'm going to get rid of some columns, and then I need to tell machine learning on Azure which things we're going to use for prediction. All right, so let's do that. The first thing I'm going to do is I am going to move some stuff out. Again, we're still on the clean transform maths part. So we'll go to data transformation and we'll go to manipulation. We're going to project some columns out. Notice how this works. It's very Windows workflowy, right? So we're going to pull some columns out. So I'm going to go here and I'm going to launch the column selector. I'm going to start with nothing and add a couple of columns. The ones I'm going to add are age, education, marital status, relationship, race, sex, and income. That's the one we want to predict. And then you run it, right? And you can keep doing this. Again, this is sort of the experimentation thing that I wanted to talk about. You'll see that a little dialog comes up here that says, hey, it's running, and then when it's done, you can see it. All right, so let's visualize it. Notice that we have our data here just the way we want. Now what we need to do is we need to change these and say, hey, this is categorical data and we want these to be part of the feature set. So to do that, right, we're going to go down and we're going to go to this metadata editor. If I may, while we're at this, notice that we have this thing called a missing value scrubber. You can go ahead and do whatever. You can replace it with a value, you can keep the column, remove the columns, or you can pretty much do whatever when you're doing missing values. You can also remove duplicate, all sorts of things. So anything having to do with cleaning data, data transformation. You can also do some really cool filters to sort of snap the bottom and the top of your data. It's actually really cool, but we're not gonna go through that right now. So I'm gonna go to the metadata editor and I'm gonna do this. I am going to launch the column selector and I am going to include age. No, age is not categorical. So education, marital status, relationship, race, sex, and income. And what I'm going to do is I'm going to say those are all categorical. So we'll go over here to this. We're going to say it's categorical. I think that's all of them. Let me remove this one, right? Because I want to make sure that I tell it also that these are features, right, of the data. Next, I'm going to go and tell it which one is the label. So I'm going to go over here. I'm going to launch the column selector, and I am going to choose, I think it was income. Hit OK, and I'm going to set it to categorical, and this one is going to be the labels, and then we're going to run it. By the way, if you have questions about this, hashtag Azure Conf to give me some questions, because let's be honest here, every time I run this thing, it's going to take at least a couple of seconds, and so I can answer questions when that's happening. All right, so there's the clock right here, and when it's done, we'll take a look at to see if we did it right. All right, so let's go here and let's take a look at the visualize. There you go. Notice that these are numerical, categorical, and then a categorical label. So I think at this point in time, we're ready to do some modeling. But remember, in order to do the modeling correctly, we have to be able to tell it how to split the data. So let's do that. Because remember, we got to have a set of data for training and a set of data for testing. And so to do that, we're going to use the split, right? So we're going to take our data and we're going to split it into two different splits. 0.8 is going to be the split that happens to the left, and then 0.2 is the one that happens to the right. Okay, so I think we're done shaping our data and doing some transformation. Now here's the cool thing. There's tons of other things that you can do to shape and to transform the data. Feel free to go in and take a look. But now we're ready to build our model, so let's do that. Remember, this area over here is for testing our stuff. All right, so let's go to machine learning and let's go to train. We want to train a model. So we'll bring this over here and then we'll bring this and hook this up. Now here's the cool thing, right? This is where we choose which model we want to use. So let's go to no, that's not. Here it is, the initialized modeling. Remember, initially when we talked about these things, we talked about that there's several types of problems. Classification and regression. There was two types of classification, binary and multi-class. And then this clustering is more having to do with unsupervised learning. We really didn't talk about that, but maybe some other time. Here's the cool thing. Let's see if I can make this bigger. There's like this one little like pixel where, there it is. All right. So notice we have a couple of them. And notice any in there that seem familiar, right? Remember the perceptron? It's there. There's a boosted decision tree, right? A boosted decision tree is like little tiny trees that are a lot of them all together. A decision forest is like if I remember right, I'll have to look. A decision forest is like a linear combination. Decision jungle is like decision trees that can go back on themselves. And then you have neural networks and support vector machines. This I didn't talk about because there's just not enough time. So let's do this. Let's go ahead and use a decision forest. And let's drop this on. All right. So how do we know how this thing is working? Well, we need to score the model. So we'll bring this over here, like so. And this little module is actually just going to score it, which will tell you, how well did it do. But then we need to visualize how it's done it and how it's done. And so to do that, we need to go in and we need to evaluate the model. And we'll bring this over here. Now, here's a cool thing, right? You'll notice right here that there's something wrong, and I'll tell you what that is in a second. But the other thing is you can actually go in here and change stuff, or label stuff so you know what's going on. So in this case, this is for the features. Okay, and this was to change the set to class. Okay, so we've got that, and then this is this. You see, and then you can, when you're looking at these things, you sort of have a better sense for what's going on, and that's a good thing. Now, what's missing? Well, let's go over here. We need to tell it what we're trying to learn. In this case, I think it's income. Now, the reason why it's not showing up there as a list is because I didn't run it. I'm trying to save some time here. So now let's run it to evaluate these models, and let's see what happens. Again, we're on step 2, right? Step 3. The first step was we have data, right? We're using the census data. Step 2 is we clean it up and get it ready for the actual models. Step 3, build the model, right? And this is an interesting step, right? Because how do we know that this is doing good? How do we know that others aren't doing good? Science, right? You use science to figure it out. And science is you guess, and then you add more things to check. Okay, so this is taking a little bit of time, and that's okay. If this was running on your local machine, it probably would crash because there's too many data points. Imagine running this with millions of points. You can do that now with the power of the cloud. Okay. Yeah, I should have warned you that these things take a little bit of time, and that's okay. In the meantime, I have some really good jokes about stuff. Oh, it's done. Thank goodness, because I was trying to think of something to say. All right, so let's go to visualize, and let's see how this model did. All right, this is called the rock curve. Anything, the area under here tells you how good things are doing. But let's focus on these numbers. These. I want to tell you a little bit about what those mean. So let's go over here, and let me show you this little. It's called a confusion matrix. So there's sort of 4 things that can happen when you're doing prediction. Over the top here, it's the truth. At the bottom here is our guess. If the answer is true and we guessed right, this is called a true positive. If the answer is false and we guessed true, this is a false positive. It turns out that all of the positive responses, the ones that we got right, that's called precision. All right. Then a recall is over here at the bottom. Of all of the really true answers, how many did we get right? That's called recall. And then for accuracy, that's all of the things that are available. How many did we get right? That's called accuracy. And so when you're looking at these things, these are the numbers that you're hitting. Now, accuracy means that we got 81% of all of our guesses right. That's really good. But how good is it? Well, I don't know. We should probably compare it to something else. So let me zoom out here and let me show you how we, this is the crazy part, right? So I'm going to grab this, Control C, Control V, and then move it over. Did you see what I just did? Now I'm going to move this over and do a scored data, move that into the scored data set. I'm going to take this class, let me go here so I don't delete everything. I'm going to take this out, and what I'm going to do now is I am going to use a different model. And this model is going to be, classification. And I don't know, let's do 2-class support vector machine. There's a number of parameters you can put in there. I'll just leave it at that. And now we're going to run it. Okay. So this might take a little bit of time, and that's okay. But the idea is that we're running this directly on the cloud. And this is the cool thing. So what I'm going to do is while this is running, I'm going to go over to the one that I've already done. Scroll down here and show you. No, that's not the one I wanted to show you. So let's go back over here and let's go to the income experiment. You can see that I've actually done a lot of them, and you can actually check and visualize how the models are doing against each other, right? Take a look at that. Right? These happen to be fairly close, and so there's not too much of a difference. This is 82% accurate. This other one is 82, and so they're all doing pretty good. Okay, so let me go back now to my robots area, and let's go to the experiments. Hopefully the experiment I was running is already done. Yes, it is, and then we can evaluate these two models together, and you can see that this one on the right-hand side seems to be doing a little bit better. So what we're going to do now is, now that we've made this model that we think is going to work, now we have to actually do the prediction. So let's do that right now. What I'm going to do now is I'm going to take this one out because we know that this one doesn't work as well as the other one. Now I'm going to move this over like so. And one of the things is you don't want to have this in production. You want to sort of have your trained model saved. And so to do that, you can create this thing called a save as trained model, and we're going to call this our income classification model, and I'm going to hit OK. All right. So now I don't need this because I have a trained model here that I can use, and I'm going to just drop this in here like so. The other thing that's interesting is when we're getting ready to deploy, we don't need to split our data anymore, right? And the other thing that's also interesting is we don't want to have to, well, I should have done this before. I need to save this income experiment to our income deploy model because I don't want to change stuff around and make my experiment all hose. So now this is I save this as a different model. And so now what I want to do is when I'm doing prediction, I don't want to have to pass in the actual class that we're predicting, and so we need to do one more manipulation, which is to project out the columns. And so we're going to do that. And what I'm going to do is I'm going to launch the column selector here, and I'm going to start with all columns, and I'm going to exclude the income, which is the thing we're trying to predict, and then I'm going to bring this in. Okay. So, input port data set is that. Well, let me go back and let me go to the playground because I don't want to fiddle. I'm running out of time. Let me go back to the experiment here on my income deploy, and here's the cool part, right? The project columns into the score model. Here's the cool part. Notice that I can set these. So let me unset these so you can see what it's like. Now what I want to do is I want to be able to use this model to do prediction. And so all you have to do is right-click and set this as the publish input. Right-click, set this as the publish output. Then you run it, right? And this is the coolest part, I think, of all of Azure ML, that once you've done all these experiments and once you've scored them and you found the one you want, you copy the experiment, set it as the deploy output, and once it's done running, The crazy part is this. Now, there is this little button that's going to light up as soon as the experiment is done, where you can publish this as a web service. There it is. This is the crazy part. Now, once you've done all of your experiments online, now you can use an API. Let's test it. You can use an API to call into this and get a prediction. So here's an example. Age 59. The education is a doctorate. Marital status is married, a civ, a spouse. That's the one thing, though. It has to match. If it gets something it hasn't seen, it usually has a hard time with it. Own child, a husband, and white. And then when I click on this, notice it's going to test it. There you go. And then the details, you can see less than or equal to 50K. And you can see that 0.09. So the way it works, that's the scored probability. And so if it's over 0.5, it's going to be positive. Over, it's pretty cool. So not only do you get a number, you get a confidence level. All right. So I think I am mostly out of time. Before I finish up, the cool thing again that you want to work on is, what if you want this to be in your actual application? You want to use this prediction in your website, for example. Well, there's an API, and seriously, all you have to do, if you cut and paste this right in, I think you have to add like a NuGet package for the Web API client. Done. You actually have the code right here to send data in. So, for example, you would just change this part to get the actual to push the values in that you want to predict, and then out will come the actual predicted value. So they're giving me the eyeball, the stink eye over there. So we did that. Free month trial. Yeah, it's pretty cool. Thank you. And again, please stay tuned to the next sessions. My name is Seth Juarez. I'm the Analytics Program Manager at DevExpress. You can reach me at Seth Juarez. If you have any questions, shoot them at me now. But again, I'm pretty excited about what Azure ML promises because now you are not constrained by RAM or by the space on your particular storage environment. It's pretty cool. You can make predictive algorithms, you can experiment with them, and then you can deploy them so that your applications can use them live. Again, thank you for watching, and please sign up and let's do some machine learning.